Okay, good afternoon. This is Professor David de los Reyes. My topic for this afternoon will be integral calculus on the topic volume, still using the circular disc method. Okay, I will give you more examples on the so-called derivation of a popular object under lower mathematics. That is, we will derive the formula for taking the volume of a right circular cone. We are done with the cylinder. Right circular cone with radius r and altitude h. Okay? Let's proceed, guys. This is now my lesson number 65 under my topic integral calculus on my channel, and the subtopic is volume, and the classification is still under computation of volume using circular disc method. Okay. I will give you another example problem. I think we are done with the right circular cylinder as per. We derived those already, the formula for taking the volume, presenting two solutions. For this afternoon, we will derive the formula for taking the volume of a right circular cone in terms of the radius r and altitude h. Okay, I will read the problem. Find the volume of a right circular cone with radius r and altitude h. I draw a right circular cone on this piece of bond paper over here. So this should be the cone. Actually, a cone is not an, it should have a volume something like that. So if you try to invert this one, actually it could contain some liquid inside. So it's a must for us in the real life that we should know what will be the volume content of this right circular cone if we are given the radius r and altitude h. So we will now derive the formula for taking the volume as a function of the radius r and h. Under lower mathematics, I think volume for a right circular cone is actually 1/3 pi r square h. This is the required volume. So by using integral calculus, we will derive this formula here. Okay, let's bring out the figure. Y-axis, x-axis, okay? This is the base of the cone, and this is the height of the cone, okay? As you see the cone from here, it seems it's a solid, okay? If it's a solid, it could contain some volume, okay? I think the only solution that we could present under right circular cone is only one solution, that is by using a horizontal slice. Okay? By using horizontal slice. Why horizontal? It's parallel with respect to the x-axis. Horizontal. Okay? So this will be the differential area. Okay, this point here will be XR, this point here will be XL, and the thickness is along the y-axis, so it should be dy. Okay, I will try to enlarge, okay, this is XR, meaning the X on the left, this is XL, and the thickness will be dy. We will try to rotate this differential slice, okay, one complete revolution with respect to the y-axis, okay, because if we try to rotate this one complete revolution, actually we are taking the volume of the right circular cone, and unluckily this differential area is actually variable. At the base, the differential is big. As it goes up, it becomes smaller, okay? So actually, we could not use a so-called straightforward solution here. We must have to use integration here to compute for the total volume of the right circular cone as this dy here moves from 0 to h. This point here should be with the coordinates 0 and h. This is h, okay? X at this is actually 0, so this is 0h, okay? If we try to figure out one vertical slice, a horizontal slice, it is something like this. We rotate it with respect to the y-axis. The radius is r, the thickness is dy, and radius r is actually xr minus xl. Okay, it's the difference of xr minus xl, because as this differential area moves from 0 to h, it varies. Okay, so I place it here xr minus xl. Try to bring out the corresponding right triangle. Actually, we could bring out the right triangle. This should be the bigger right triangle. It is 1/2 of the right circular cone. And at this point here, it refers to this, xr and xl. This point here, I place it with the coordinates xy. This side of the cone is actually a slanted straight line. And actually, there's an equation for that one, okay? So this will be r now. This is x. This is y. This is h. So this one will be h minus y. Okay? I will, this is theta, same angle. Okay? Horizontal, this is one straight line. So if this is angle theta, this angle theta also. Okay? Taking the tangent of this angle here by using the definition, tangent of theta is actually opposite side of the adjacent side. Taking the tangent of theta using the smaller upper right triangle, the upper one, this one. It should be h minus y over x. It should be h minus y over x. And by using the bigger triangle, it's h over r. It's h over r. Okay? Then you could remove this one now. So actually, we are now given an equation involving h, r, y, and x. We need to get the correct relation from the figure. Okay? Simplifying this one now, cross multiply. Okay? R times h minus y equal to hx. hx. xr now, we multiply both sides by 1 over h. Right? So what remains on the right hand side will be x. And I will now place the proper subscript. That is actually xr. It's the variable abscissa of the inclined side of the cone. What will come out on the left hand side after rearranging, this will be r times 1 over h. This is r over h times the quantity h minus y, equation number 1. That's the equation of xr as a function of radius, altitude, and y. What is xl? Xl, if you want to try to see it out from the figure, this is xl. And as we can see it, as for this dy to move from 0 to h, this xl is not changing. It's variable. And actually, we know the equation of that one. It's a vertical line. The equation of a vertical line is xl equal to 0. Equation number 2. Luckily. Okay? This is a constant xl. This is a variable xr. Okay? Y variable, see, it got y over here. xr as a function of r and h and y. It varies. But for xl is equal to 0. It does not vary as dy moves from 0 to h. So I place it here, xl equal to 0. So actually, this is your problem when you're solving the problem. You must have to bring out the correct relation of XR and XL in terms of the given variables. Okay, let's compute for the differential volume. Differential volume will be equal to differential area times thickness. The volume of one circular disc is actually the area of the circle. It is pi times the quantity XR minus XL quantity square. The difference of XR minus XL is the variable radius, okay? Quantity square. Thickness is dy. Substituting values, this should be pi r over h times quantity h minus y, this is minus 0 raised to the second power. This is actually 0, so we could remove this one now. Therefore, differential volume will be, we square all terms inside, okay? So r over h quantity square, this is r square over h square, I bring it out already, times pi, times the quantity h minus y quantity square times dy. This is now actually a differential equation. Okay? And to bring out the relation of volume in terms of radius and h, we must have to integrate both sides. That's why our topic for the meantime, guys, is integration. Let's place the lower limit. Lower limit will be 0, upper limit will be h. Actually, our limit is y, okay? Because it moves from 0 to h, okay? So, y lower is actually 0, y higher is equal to h, okay? So, integrating both sides from the resulting differential equation, the integral of differential volume equal to the integral from 0 to h. I am following this one. Pi r square over h square times the quantity h minus y quantity square times dy. These are all constant. We bring it out. Volume now will be pi r square over h square, the integral from 0 to h of h minus y quantity square times dy. Actually, you could expand this one before integrating, or you can integrate this one now, but we must have to verify something, okay? And here, it falls under the power formula. The value of u is the one inside, so u is actually h minus y. du is actually 0 minus dy, or du is equal to minus dy. It is almost exact, except for the negative sign. Right? It is exact to be under the power formula, except for the negative sign. So, to integrate it, volume now will be pi r square over h square. We place a negative 1 outside. The integral from 0 to h of h minus y quantity square times the complete differential as per verification minus dy. After placing this negative sign say over here and negative sign outside, this now falls under the power formula. So volume now will be equal to, since this is a negative 1, this is negative pi r square over h square times the quantity h minus y to the third power over 3 with the limit from 0 to h. This is negative sign, guys, but don't be afraid with the negative sign. There is no such thing as negative volume. Later on, the volume will come out positive. So volume now will be negative pi r square over h square. Okay. If we place the upper limit, this will be h minus h. Okay. So it will be 0. Raise that to the third power, it will still be 0. Divided by the 3, it will still be 0. So if we place the upper limit, the value is actually 0. And if we try to place now the lower limit, this is h minus 0. Okay? H minus 0 is actually h. We raise that to the third power over 3. So this is actually minus pi r square over h square times the quantity 0 minus, there's a minus here. That's why I told you don't be afraid with the negative sign. It will come out positive. Minus h cube over 3. Okay, simplifying further, we show the cancellation. Volume now will be pi r square over h square times the quantity. H cube is actually, this is minus and minus, so this will now be plus. Okay? And I will place h cube to be h times h square. So this h square cancel with this. So the final formula on how to take the volume of a right circular cone in terms of radius r and h is actually volume equal to 1/3 pi r square h. It's positive, guys. Because this was negative, when we subtract the lower limit, there is a negative sign, and a negative, it will come out positive. Okay, there is no such thing as negative volume. But we were able to try to eliminate that negative sign by, okay, this negative and negative, it will come out positive. So volume now will be 1/3 pi r square h. Okay, that's the complete derivation of the formula for taking the volume of a right circular cone in terms of the radius r and h. It is 1/3 pi r square h. Okay, good afternoon, Los Angeles.